I'm pumped to have you all here. Look, as mechanics and technicians, you guys are absolutely the front line of engine health. So, today, we're going to put on our lead engineer hats and dive deep into the real, unfiltered technical reality of fuel octane. We're doing this explainer so you can walk back out to your bays, diagnose engines faster, and educate our customers with total confidence. Let's get right into it. Okay, so we're going to tackle this massive misconception right out of the gate. You know the one. I know you hear it literally every day on the floor. A customer rolls in, practically bragging about filling up with 98 octane, totally convinced it's some sort of magical, power-adding steroid for their standard engine. Well, we're going to tear that myth apart today. We've got a lot to cover. We're looking at the actual physics of octane, how engine compression and the ECU handle it, the raw chemistry of high-octane blends, tearing down those premium fuel myths, and then giving you a rock-solid diagnostic playbook. Let's kick things off with Section 1, the physics of octane. And remember, it's all about resistance, not energy. All right, so you'll see these global measurements on spec sheets and service manuals all the time. First up, RON, or Research Octane Number. That's tested in controlled, low-speed lab conditions. Then you've got MON, the Motor Octane Number, which is way harsher testing under high-speed, high-load conditions. And if you're ever looking at an American or Canadian service manual, you're going to see AKI, or the anti-knock index. That is literally just the mathematical average of RON and MON. So practically speaking, a 91 AKI pump rating over there is roughly the exact same thing as a 95 or 96 RON everywhere else. Now let's talk about public enemy number one on the shop floor, knock. In a healthy cycle, the spark plug fires and that flame front expands nice and smoothly to push the piston down. But knock, or detonation, is when that air-fuel mix gets squeezed so hard it auto-ignites before the spark plug even does its job. You get a violent second flame front that crashes right into the primary one. That collision spikes the cylinder pressure, giving you that awful metallic pinging sound you've probably heard. And worse, it destroys pistons and bearings. Remember, an octane rating is simply a measure of how well a fuel resists this exact disaster. As techs, you've got to know the difference between knock and pre-ignition. They are not the same thing. Knock happens after the spark fires, it's spontaneous combustion of the end gas. Pre-ignition, though, that's when a random hotspot like a glowing chunk of carbon or a severely overheated exhaust valve lights the mixture way ahead of the spark. Pre-ignition is a total nightmare. Under heavy load, it causes catastrophic piston holing almost instantly, usually before the driver even realizes something's wrong. Okay, moving to Section 2, let's look at how engine compression and the ECU step in to manage all this pressure. It all really comes down to compression ratios. Take a standard naturally aspirated engine with an 8 or 9 to 1 compression ratio. Cylinder pressure is relatively low, right? So it runs perfectly on regular 91 RON. It has plenty of knock margin. But what if a customer brings in a modern turbo or supercharged engine pushing, say, 2 bar of boost? That forced induction is just cramming massive amounts of air into the cylinders. The effective pressure absolutely skyrockets, generating intense heat. For that engine to survive without detonating itself to pieces, it absolutely needs the resistance of 98 to 100 RON fuel. So what actually goes down inside the ECU when that turbo customer accidentally fills up with cheap gas? Well, modern engines have a built-in survival instinct. They use these piezoelectric knock sensors bolted right to the block, just listening for the specific vibration frequencies of detonation. The absolute millisecond the ECU hears knock, it jumps into emergency mode. It immediately pulls ignition timing back by 2 to 4 degrees, dumps extra fuel in to cool the combustion chamber, and it might even electronically cut the turbo boost. Once things quiet down, it'll slowly try to creep that timing back up. And that's exactly why modern cars don't just grenade themselves on cheap fuel. But hey, that digital safety net, it comes at a cost. When that car limps into your bay, the customer's going to complain about sluggish throttle response and terrible gas mileage. Why? Because pulling timing aggressively absolutely kills combustion efficiency. A car tuned for 98 RON that's choking on 91 can easily lose 15 to 30 horsepower, and the torque curve just goes totally flat. The engine is saving its own life, but it's bleeding performance to do it. Let's jump to Section 3 and peek inside the chemistry of these high-octane blends and race fuels. This one usually shocks people. Chemical blending, like throwing E10 ethanol into the mix, is a cheap way to raise the octane rating. Pure ethanol actually sits around 108 RON, but here's the catch. Ethanol actually has roughly 34% less raw chemical energy per liter than pure petrol. So yeah, it boosts knock resistance, but it literally drops the raw energy content.
This is exactly why you'll see fuel economy take a slight hit on high ethanol blends. Guys, high octane does not mean high energy.
You'll also see refineries dumping in aromatics, chemicals like benzene and toluene, to build up that anti-knock shield. Toluene is crazy high, boasting a 121 RON. But just like ethanol, these aromatics carry less oxygen, which slightly drags down combustion efficiency compared to standard fuel. This completely shatters the myth we talked about earlier. Octane reading has absolutely nothing to do with increased chemical energy density. It's just a heat threshold. Think of octane as a fire-retardant coating, not rocket fuel.
And inevitably, you're going to have that guy asking if race fuel will make his street car faster. Just politely remind him that pump premium and true race fuel are totally different animals, even if they both say 100 RON on the pump. Real unleaded race fuel has incredibly tight batch consistency and specific oxygenates meant for a rich, high RPM burn. Pump fuel? It varies wildly depending on the season and the station. Race fuel won't magically make a stock road car faster, but for a high-compression, purpose-built track engine, it's mandatory for survival.
All right, Section 4. Time to debunk those premium fuel myths and separate fact from fiction. I'm putting this quote right up here because it is the absolute biggest illusion we face. Repeat after me. High octane is a protective shield, not a power-adding steroid. Unless an engine is mechanically knock-limited by high compression or forced induction, high octane gives you literally zero power benefit. A physical engine cannot magically exceed its own thermodynamic design just because you poured more expensive liquid into the tank.
Let's kill a few more myths while we're at it. Customers love to say premium cleans their engine. Nope. If they want clean valves, they need dedicated detergent additives, not just a higher octane number. You'll also hear it burns cooler. Again, no. Combustion temperature is dictated by the air-fuel ratio, the stoichiometry, not the octane rating. And better fuel economy? In a standard engine, it's going to be exactly the same. Any difference they feel is 100% psychological.
The absolute bottom line here is this. Putting 98 RON in a totally stock, unmodified economy car that's factory mapped for 91 is literally just setting money on fire. The ECU only has a base map. It cannot magically advance the ignition timing past its pre-programmed factory limits just to exploit that premium fuel. So that super expensive extra knock resistance? It's just unused overhead blowing straight out the tailpipe.
Let's bring this all home with Section 5, Shop Diagnostics and Customer Chat. This is your technician's playbook for the bays.
When a car rolls into your bay, I want you to look for the evidence. If the customer is cheaping out and running fuel below the factory spec, the engine will tell you. You might actually hear it pinging under heavy load. The customer's going to complain the car feels sluggish, and if you pull up live data, you'll see elevated exhaust gas temps. Most importantly, your scan tool is going to catch the ECU aggressively pulling timing to save the engine. So here is your step-by-step diagnostic flow. 1. Check the manual and verify the actual factory requirement. 2. Plug in your OBD scanner, go for a drive, and look for logged knock events and timing retard under load. 3. Think about your environment. High altitude means thinner air, which actually lowers cylinder pressure, so sometimes cars can actually tolerate lower octane up in the mountains. And 4. Simply ask the customer what fuel they pumped. Use this flow, and you can mathematically prove to a customer if they genuinely need an octane upgrade or if the engine is running totally fine as is. Here is a cheat sheet you can use every single day to spot customers who are pointlessly inflating their fuel bill. If their manual says regular unleaded and the engine is unmodified, they're wasting cash. If they drive a diesel which uses compression ignition, meaning octane literally doesn't even apply, they are completely lost. And if they're buying premium purely because they think it cleans the engine, stop them and sell them a proper bottle of fuel system cleaner instead. They genuinely need your technical guidance here. So how do we actually talk to them about this? I want you to memorize this exact script. When you get a customer who's confused or a little skeptical, look them in the eye and say, High octane is a protective shield against heat, not a power booster. Let's stick to the owner's manual and we can use a separate, dedicated detergent additive for cleaning. It's professional, it's incredibly clear, and it explains the physics without making them feel foolish for falling for a marketing gimmick. I'm going to leave you with one final thought before you head back to the floor. We've just proven that Octane is an enabler. It unlocks high-performance designs, but it doesn't create power out of thin air. So as mechanics, when a customer shows up with some expensive new hardware or fancy fuel, you have to ask yourself, can this engine's management system actually utilize what they just bought, or is it just more useless overhead?
Keep questioning, trust your scan data, and let the physics guide your wrenches. Thanks for joining this explainer, guys. Get out there and crush it in the bays.